Hi, this lesson is about the limit of a function. So before we start talking about limits, let's remind ourselves what a function is. So a function is a relationship between two variables where for every value of the independent variable, which we usually call x, there is only one corresponding value of the dependent variable, which we usually call y. Typical notation used with functional notation is f of x, and so y and f of x, they mean the same thing. It is the value of y when x is a particular value. So here's an example. We have this cubic function, f of x equal to x cubed minus 1. And if I wanted to evaluate f of negative 2, that means negative 2 gets substituted in where the x is. So it's negative 2 to the third power minus 1, which gives us a result of negative 9. So your inputs could be variables themselves like this. If x is equal to a, then f of a would just be a cubed minus 1. So remember, there are different types of functions. So a few examples would be linear functions, quadratic functions, rational functions, and square root functions. There sometimes a relationship between two variables are not functions, and that's just called a relation. So for example, y squared equal to x squared, this is not a function because for every x value, there could be more than one corresponding y value. So for example, if x is equal to 1, then y could equal plus or minus 1. So it doesn't satisfy the definition of a function, but it is considered to be a relation. So functions have domain and range. So the domain is the set of all possible values of real numbers for the independent variable, and the range is the complete set of all possible real number values for the dependent variable. So when we're considering domain and range, we want to make sure that we are avoiding numbers that give us an imaginary number result or that result in division by 0, because that is undefined. So here are a few examples of domain and range. So here's your common function, your basic quadratic f of x equal to x squared. All quadratic functions have a domain of all real numbers, but your range with quadratics depends on where the vertex is on the parabola and the direction that the graph is facing. This is an upward facing parabola with a vertex at 0, 0. So your range is going to be from 0 to infinity. Here's two different notations. Set builder, f of x is greater than or equal to 0. And with interval notation, it's the square bracket 0 to infinity, which means include 0 in the range, and then all values greater than 0. Okay, so in the next example, this is a rational function. Oftentimes with rational functions, you do have a restriction on the domain because you want to avoid values of the independent variable that result in division by 0. So in this case, when x is negative 2, this would be undefined. So your domain is the set of all x such that x is not equal to negative 2. Or in interval notation, it is a union of two intervals. It's from negative infinity to negative 2 with a parentheses around the negative 2, and then from negative 2 to infinity. And the parentheses means do not include the number. So parentheses means something different than the square bracket. So in this case, we also have restrictions on the range. So y will never equal 0. So it is the set of all y such that y is not equal to 0, but it could be positive and negative and all values in between. Or in interval notation, it is from negative infinity to 0, union from 0 to infinity. And this last example is a square root function. With square root functions, you want to make sure that your domain only reflects values that give you a real number result when you take the square root of it. So in that case, your x has to be greater than or equal to 2, because anything less than 2 you would have a negative inside of the radical, and a negative number inside of a radical is imaginary. So it is the set of all x such that x is greater than or equal to 2, or square bracket 2 to infinity. And then your range, you're never going to get a negative result here, again, because if it was negative on the inside, it would be imaginary. So it is from all values greater than or equal to 0, or from 0 to infinity. Obviously, when x is equal to 2, which is in the domain, this would be the square root of 0, so the value is 0, and then anything greater than 2 would give you a positive result. All right, so let's talk about limits. What is a limit? So this is the notation used. This is read as the limit of f of x as x approaches a equals L. So what it means is that the closer that x gets to this number a, so a would be some value on an x-axis if you were reading a graph, then your f of x is getting closer and closer to some value that we're calling L. So that would be a value that you would be reading off of the y-axis. And when we say getting closer and closer to a, we mean from the right side and from the left side of a. So again, if you imagine a being on a number line, the horizontal axis, from the right of a means values greater than a, and from the left of a means values less than a, but very close, meaning like within a couple of decimals of each other. So here's an example of how to evaluate a limit numerically. When you're evaluating a limit numerically, you're going to need a calculator to do that type of work, because these will be very numbers with a lot of decimal points in it. So we want to evaluate the limit of this rational function. I have a cubic in the numerator and x plus 3 in the denominator. So we know that the function itself is not defined at this value -3, because if I were to plug that in, I would have division by 0. But that doesn't mean that the limit won't exist. So in order to evaluate the limit, we look at values close to -3 to the left of -3, which means less than -3. So these are 3 examples of how we're getting closer and closer to -3 from the left. So I start at -3.1, then I go to -3.01, then I go to -3.001. So they keep getting closer and closer to -3. These f of x values is the result of plugging in the numbers above into the function. So for example, for -3.001, that number was replaced all of the x's, and when you compute that, you get that the y value is 13.007. And you can see that all of the y values seem to be getting closer and closer to the whole number 13. If I perform the same exercise to the right of -3, that's this side, the furthest one away from -3 is -2.9, that's to the right of -3, then -2.990, and then -2.999. So again, the closest one is the one here in the middle, -2.999. And when I plug in those 3 numbers, for example, this one, if I plug in -2.999, I get a y value, or f of x value, of 12.993. So the closer x gets to -3, it appears that f of x is getting closer and closer to 13. So that's exactly what we state, that this limit is equal to 13. All right, so here's another example of how to compute something numerically. We have the limit as t approaches 0 of sine of t over t. So again, sine of t over t is not defined at 0, because I would be dividing by 0, but that doesn't mean that the limit does not exist. So here's another table. So I'm showing you more numbers to help you see what happens as you get closer to 0. This set here are the numbers to the left of 0. So you can see I start at negative 0.1, and then I'm getting closer and closer to 0, finally with negative 0.001. The y values you would need to plug into a calculator, and you would get these values here. So it looks like, at least from the left side of 0, that my y values are getting closer and closer to the number 1. And if I do the same thing to the right of 0, so 0.1 being the furthest one away, and 0.001 being the closest one, and these were the right side and the left side of 0. So as I get closer and closer to 0, it appears that my y values are again approaching 1. So these are the two that are closest to 0, and you can see that the y value seems to be getting very close to 1. And so therefore, you can assume that the limit as t approaches 0 of sine of t over t equals 1. So now let's look at different scenarios that could occur with limits. So these two numerical examples, I showed you that the limit exists, but the limit won't always exist, and there'll be different scenarios to consider. In the first example, the limit as x approaches a of f of x equals L, but in this example, f of a is defined, it's in the domain, and f of a equals L. That's the simplest of all the scenarios. The two I did above do not satisfy that first scenario because, just as a reminder, 0, that function does not exist at 0. So f of 0 would not be defined. But that numerical example is more like this scenario where your limit as x approaches a of f of x equals some number L, but f of a does not exist. So that's exactly what we found in the previous two examples. We found a limit value that exists, but your function does not. And then with this third scenario, this happens often with piecewise functions. We have a limit that exists, but f of a has a different value. It could also happen with rational functions. So we'll see some examples of that. And then in your fourth example, well, the limit simply just does not exist, and there'll be different reasons why that happens. For a limit to exist, it has to be a finite number that we're calling L. It can't be going to positive or negative infinity. And the limit from the left and the right side of A have to be going to the same number L. So, which leads us to more definitions. We have something called one-sided limits. So when considering the limit of a function from one side, meaning the left side or the right side, we call those one-sided limits. And so there's special notation for that. This one right here is the limit as x approaches a from the left. So when you have that little minus sign on the right side of a, that means a from the left. It doesn't mean negative a. A could be positive or negative or 0. But when you put the minus sign on the right side of it, of that number, it means it's approaching it from the left. And when you have the limit as x approaches a from the right, you'd be putting the little plus sign to the right of a, and that means you're getting closer and closer to a on the right side of a, meaning your numbers are greater than a. And so now that we know what a left-sided limit and a right-sided limit is, the actual definition of the limit is that a limit exists if and only if the limit as x approaches a of f of x equals a from the left of f of x equals L, and the limit as x approaches a from the right of f of x equals L. So they must both approach the same number L on the left and the right side of a in order for you to state what the limit is. All right, so we're going to do examples of the 4 scenarios that I just stated. And we're going to start with a graphical example here. So scenario number 1 says that the limit as x approaches a of f of x equals L and f of a equals L. So both the limit value and the function value are the same. So here we want to evaluate the limit of this graph as x approaches 2 of f of x. So when I get closer and closer to 2 on the left and the right side of 2, if I follow the path of the graph on the left side, it appears to be going towards this hot pink point, which has a value of 3. And as I get closer and closer to 2 on the right, so this being the right side, and I follow the path of the graph, it also appears to be approaching that number 3. So my limit value as x approaches 2 is 3. But it's also defined at 2 to have a value of 3. So f of 2 is also 3. So both the limit and the function value are the same. That's the simplest of all of your scenarios. Here's another example of scenario number 1, done numerically, meaning with tables and using all these decimals. I want to evaluate the limit as x approaches 1 for x squared minus 1. So just like I did in the other examples, I picked values to the left of 1, and I picked values to the right of 1, and I plugged it into f of x, which is this, and I got my y values in that second table. And it looks like when I'm getting close to 1, it appears that these numbers keep getting closer and closer to 0 on both sides. So my limit value is 0, but my function, if I plug in f of 1 into my function, 1 squared minus 1, it's in the domain, 1 is in the domain, is also equal to 0. So we have a limit value and a function value that are equal. Okay, so that's our first scenario. So now we move on to scenario number 2. That's the scenario where the limit as x approaches a of f of x equals L and f of a does not exist. And that just means that a is not in the domain of your function. So here's a graphical example. I want to evaluate the limit as x approaches 3. So I'm on the left side of 3, and I'm following the graph, and it appears to be approaching this open circle, which corresponds to the value 4. When I'm on the right side of 3, and I follow the path, I also seem to be approaching that same open circle, so my limit is 4. So it doesn't have to equal 4, it just has to be close to 4. But then, if I look at this function and I say, well, what is f of 3? You can clearly see that when x is 3, your y is undefined. So it's an example of where the limit exists, but your function does not. So scenario number 2. All right, so here's a numerical example of scenario number 2, where your limit exists, but your function does not. So again, I'm using these tables. I picked numbers from the left and from the right, and I plugged into my y values. And so as I'm getting closer and closer to 1, which is what my limit is approaching, it looks like my y values are getting closer and closer to 2. So I think it's pretty safe to say that this limit, as x approaches 1, is equal to 2. But if I plug in 1 into this function, it's undefined, right? You would have division by 0, it's undefined. So it's again another example of where the limit exists, but the function does not. Scenario number 3. We have the limit as x approaches a of f of x equals L, and f of a is not equal to L. So what this means is that your limit exists and your function exists, but they are different. And this does happen often with piecewise functions. So if we consider this limit, the limit as x approaches 1 of f of x, when I'm on the left side of 1 and I follow the path of the graph, I seem to be approaching that open circle, which is going towards -3. When I'm on the right side of 1 and I follow the path of the graph, I'm also approaching the same value. So my limit is -3. But if I read the graph and I say, well, what is f of 1? You can see that I have a solid point up here at 2. So f of 1 is 2. So it's an example of where the limit and the function value both exist, but they are different. So here's another example. I have the limit as x approaches 1 of g of x, and g of x is defined to be this piecewise function. So g of x is x squared minus 1 over x minus 1 when x is not equal to 1, but it's equal to 3, meaning the y value is equal to 3 when x equals 1. So you might recognize this, the first part of this function. It's the same one I did up here. So we already know that that limit as x gets closer and closer to 1 is 2. So I didn't rewrite the table for you. So the limit is equal to 2, but g of 1 is equal to 3. We get that from here. So it's again an example of where the limit exists, but the function value exists, but n is different. The graph is here. So you can see that as I get closer and closer to 1 on the left and on the right, my path is approaching that open circle. But when x is equal to 1, right here, your y is equal to 3. Okay, and now let's move on to the last scenario, which is the limit doesn't exist. So there's many reasons why the limit wouldn't exist. One is if it doesn't converge to a finite number. So here's an example. I have f of x is equal to 1 over x squared. This is my graph right here. If I wanted to compute the limit as x approaches 0, as I get closer and closer to 0 on the left and on the right side of the function, this is the left and this is the right, and if you follow the path, you can see that on both sides, this is approaching infinity. Infinity is a concept. It's not a finite number. So although it's nice to know what the behavior of the function is, it means that the limit does not exist when it doesn't equal a finite number. Another example is this one here. This one actually has a special name. It's called the Heave side function, and it's supposed to represent a light switch. So I have h of t is equal to 0 when t is less than or equal to 0, meaning the switch is off, and h of t is equal to 1 when t is greater than 0, meaning the switch is on. So if I wanted to compute the limit as t approaches 0, by the way, here's the graph. 0 and 1 are constants, so they're just two horizontal lines. So when t is less than or equal to 0, that's this part of the graph, and when t is greater than 0, that's this part of the graph. I have a closed circle here because of the less than or equal, open circle here because it's just greater than for the second part. Okay, so if I wanted to compute the limit as t approaches 0 from the left side, I'm here. This is the left side. You can see that h of t is going towards the origin. But when I am on the right side of 0, this side, and I follow the path of the graph, it is going towards 1. So since the limit on the left side and the right side are not the same, it doesn't satisfy the definition, and therefore the limit as t approaches 0 of h of t does not exist. DNE means does not exist. Okay, so that's it for this lesson. I'm doing this section in 2 parts. This is part 1. Stay tuned and check out part 2. Thanks.